Hey everyone. Today's lesson is going to be on the pH scale, which most of you are probably familiar with, having seen it or at least heard about it in probably a number of different situations. And you might feel like you have a pretty good idea of what it is, and maybe you do. Maybe you have no idea what it is. Maybe you've heard of acids and bases before, which, this being our third lesson in this unit, hopefully you would have heard that already. But this is more common than you think. And pH has to do with the hydronium ion, which we first learned about in our first lesson in this unit, which generally will indicate that a substance is an acid, and we can then use some of that information to relay what we can figure out about the hydroxide ion concentration. And we'll connect both of those to the pH scale. So at the end of this lesson, you should be able to identify a solution as either acidic, basic, or neutral based off of the pH of that substance. Now, water, we had mentioned before, dissociates or breaks up into two different ions. And this happens very slightly in distilled water or in pure water. So water will break up into two different ions, or H plus, which we can also refer to as the hydronium ion, or OH minus 1, which we know as the polyatomic ion called hydroxide. And in neutral water, the concentration of these two ions, hydronium or H plus and hydroxide, are going to be the same. And in neutral water, if we just look at H plus, the concentration is 1 times 10 to the minus 7th power molar, which means the pH is 7. And when we talk about pH, we're talking about the concentration of hydrogen. That's why we refer to the concentration of hydrogen, or H plus, when using or figuring out our pH. And these two are connected. Now, I feel like this graph kind of gives a lot of information here, so I'm going to try and break this down as clearly as I can. We have two different ends of our pH scale. One's down here, which are considered our acids, and 14 on the right, which is considered our bases. And 7 is neutral. So if you have a pH of 7.1, the solution is slightly basic. If you have a solution with a pH of 6.9, the solution is slightly acidic. Now, on both sides of this graphic here, we have two different concentrations. One is the concentration of hydroxide ions, and the other is the concentration of hydronium ions. The gray side here indicating hydronium, and the white side showing hydroxide ion concentration. And as the pH increases from 1 up to 14, we see the concentration of H3O plus go down and the concentration of hydroxide go up. And this is as we kind of see the line here moving slantwise from left to right as the concentration of hydronium decreases and the concentration of hydroxide increases. As these exponents get smaller, so they're getting more negative, we see the pH getting higher. And as the pH gets higher, we see the concentration of hydroxide getting larger. Now, one thing I want to point out here, when we have a pH of 7, we see that the concentration of our hydronium is to the power of negative 7. When the pH is 8, we have a hydronium concentration to the negative 8th power. So the pH is connected to the power of 10 in regards to the concentration of hydronium. So we would have a hydronium ion concentration to the minus 14th power. Our pH is going to be 14. So we can also look at the pH scale. We always look at it as pH in regards to hydronium, but we can also look at a solution's pOH, which really is just looking at the concentration of hydroxide ions in the solution. So in this case, if we were to have, let's say we had a hydroxide ion concentration to the minus 10. The pOH would be 10, while the pH, see that there, would be 4. So these are just kind of indicating the concentrations that we're referring to in the name. And these numbers are always going to add up to 14. And we can look at that anywhere on the table. Negative second power plus the negative 12th power gives us 14. 10 to the 0 and 10 to the 14 gives us 14. 10 to the negative 12 and 10 to the negative 2 gives us 14, and so on. Now the concentrations here are indicating whether something is more basic or more acidic, but we always are going to have a concentration of hydroxide, even if it's infinitely small, and the same thing with our concentration of hydronium. It may get infinitely small or infinitely big, but they're always going to be there. So the number of hydronium ions as we decrease pH, now I think some of this wording is always confusing. As we decrease in pH, the number is decreasing or getting smaller. And as we decrease in that, the number of hydronium ions indicated here, they're getting greater. The number is getting more positive or less negative. As we just said, is there ever a total absence of hydroxide or hydronium? There is not. It's infinitely small or infinitely large. So when we add an acid to water, we increase the hydronium ion concentration so that the pH increases by 1 as the acid strength increases tenfold. So what this means, when we have an hydronium ion concentration of 10 to the minus 1, the pH is going to be 1. And if we increase the pH or the acid strength by tenfold, or to the minus 1 power to the minus 2, the pH is now 2. So our pH is changing by 1 value, but the difference in our concentration of hydronium is tenfold, or 10 times as much. So when the hydronium or H plus concentration is to the minus 3, our pH is 3. So every time our pH is increasing and decreasing by 1, the concentration is increasing or decreasing by a tenfold margin. And the last one here, 10 to the minus 4, would be a pH of 4. So how different are they really? Well, a solution with a pH of 3, and this is going to be kind of wordy, so stick with me, it's 10 times more acidic than a solution with a pH of 4. So as this number decreases to 3, the pH gets smaller, it's actually 10 times more acidic. A solution with a pH of 3 is 2 integers away from 5, and each change of 1 pH is a 10 times fold increase or decrease in the concentration of hydronium. So from 3 to 5, this is 10 times 10, or 100 times more acidic. And if we compare a solution with a pH of 3 to one with a pH of 6, the pH of 3 is 1,000 times, or 3 to 4 to 5 to 6, 10 times 10 times 10, 1,000 times more acidic than a solution with a pH of 6. Now, to kind of run through a couple examples of different substances on the pH scale, I'll start with the two extremes, at least listed on this graphic. Sodium hydroxide, considered a very strong, one of the strongest bases, and hydrochloric acid, being our stomach acid, not necessarily upset stomach acid, is going to be one of our stronger substances as in regards to pH. And yes, we can have a value here of 0, which this is actually going to be slightly stronger than our actual stomach acid, but HCl is what we'd find in our stomachs. Now, as we increase in pH, as the number gets bigger, we're decreasing the concentration of hydronium. So from left to right, as we move from left to right, that concentration of hydronium is decreasing, and as that happens, the concentration of hydroxide is increasing. So bleach, and we notice here on the basic end, bleach, ammonia, non-phosphate detergents, borax, detergents, baking soda, these are all things that are used for cleaning. Most cleaners are going to be on the basic side. And on the more acidic side, we can see at neutral here, we have milk. Human saliva is roughly a pH of 7. Same with blood or pure water. It's right about 7. I think the blood and saliva might be slightly basic. Normal rain we can see is slightly acidic. And then a lot of the stuff in the acidic portion here, orange juice, for those of you that drink sodas, tomatoes, bananas, coffee, potatoes, salmon, bread, are all slightly acidic. And there are a few foods that are basic. Eggs, at least listed on here. Milk, I believe, is slightly basic. Just a few examples there of the pH scale. And we're going to take a look at this in a second, but this is kind of a quick little summary slide of the pH scale, which, again, doesn't always show the concentration of hydroxide, but we can always kind of pull that from the scale if we know the hydronium or H plus concentration. Our concentrations are always going to add up to 14, and that's going to be the absolute value, so not negative 12 plus negative 2, but 12 plus 2. Those are always going to add up to 14, and that's going to indicate to us, in this case, this would be a pH of 12, which would be very basic. This would be a pOH of 2. We'll take a quick little look here at the simulator on the PhET website, which I encourage you to take a look at and play around with a little bit. And we'll look at this real quick here. So we have water. We have a container. We can drain some water out. We can add some water to it. And if we bring the meter into here, we have a pH of 7. And if we add more water, pH isn't changing. The water in the dropper here is a pH of 7. So if we add a pH of 7 into a solution that has a pH of 7, it's just going to remain the same. Now we'll look at, let's do soda pop, because I always find this pretty interesting. Whatever we add here in regards to soda pop is going to have the same pH as this solution here. So we bring the meter in. Our soda pop has a pH of 2.5. Pretty acidic. Now if we drain some out, the pH remains the same. But if we add water, we'll see that the pH starts to rise, and this is getting more basic. I want you to think about why that's happening. And if we drain this out, it stays the same. But if we add more acid, it's going to make it more acidic. and vice versa. We add more water, it'll make it more basic. Now something like drain cleaner, again, most cleaners are going to be slightly basic or heavily basic. In this case, we have a pH of 13, so that's very basic. And if we add more drain cleaner, pH stays the same, but if we add water, it starts to decrease. So what's happening when we do this, if we add water to a solution with a pH, in this case 13, we start to dilute what was already in our container. And what's coming out of here is PO, or not POH, but hydroxide and hydronium ions in equal concentrations into this container, which is making the overall ratio of pH to OH more even. That's why we start to see, if we add more water to this container, we start to see our pH come down towards the middle of the scale. And if we were to continue to do this on either the acidic or basic end, our pH is going to continue to move to 7 roughly, because that's what's coming out of the faucet here. Now we'll connect one more thing on here, and we'll do this with water for now. We have a pH of 7, but on the side here we have concentrations of 3 different substances: water itself, the hydroxide ions, and the hydronium ions. And we see here that we have 10 to the minus 7th power and 10 to the minus 7th power of both hydronium and hydroxide, which is going to make our pH 7. Now if we look at something that is, let's go back to the soda pop. We have a lot more hydronium than we do hydroxide. And hydronium concentration is 3.2 times 10 to the minus 3rd, which gives us a pH of about 2.5. These don't always exactly line up, but this would round up to about 3, which would match up with our minus 3 exponent there. We can look at a ratio of these 2 ions together, and we can see that there's mostly hydronium in the container here, and we have a couple hydroxides in that solution. But what makes soda pop so acidic is this heavy concentration of hydronium ions. And if we add more water into this, we're going to start to dilute the solution. And since the pH of water is about 7, we're going to see our pH start to rise. And we have a similar ratio. We have a couple more hydroxides that weren't there, 2 compared to 5 now. And we see our pH start to change. And we can watch the values move on the chart on the left here as we add water. And these two are going to start to move towards each other, albeit pretty slowly, until they meet the pH of the water. We can look at molecule count. And now when we decrease this, or we add water, we can see the water concentration and the hydroxide concentration changing much faster than the hydronium ion concentration. With drain cleaner, we see we have a much higher concentration of hydroxide. That's why we get a pH of 13. And the pH number is coming from the concentration of hydronium, which is 10 to the minus 13th power. So the key here in all this is that the pH is indicating the concentration of hydronium. The higher that concentration is, the higher our pH, or excuse me, the lower our pH. Higher concentration of hydronium, lower pH, so a number like 1 or 2. A lower concentration would indicate a higher pH like 13 or 12. If you guys have any questions, make sure you write them down and seek out a question or seek out an answer to your question. Hope you guys have a great day.